The recent enablement of EQ or equatorial mode tracking in the Seestar smart telescopes by ZWO has caused quite a stir in the astrophotography community. Of course, I too downloaded the app and tried it on the first possible clear sky night. All of the early YouTube video reviews talk about the benefits of EQ mode and walk you through the new app. However, in this video, I will mostly focus on how it works, what issues you are likely to encounter, how to deal with these problems, and tips to maximize your success. In addition, I tested an alternative polar alignment technique using a classical polar scope to see if that offered any benefits. Let's dive in. What is special about the Seestar smart telescopes is that you really don't need much equipment. All you need is a smartphone or tablet, a tripod, and for EQ mode, a Latitude base or something similar to incline your Seestar. Here you can see my setup at the nearby Kawawa Fuji Park. The angle of inclination is around 35 degrees, matching to my latitude here in Yokohama. I now routinely use this Jaiwen XH Star Latitude base that I bought on AliExpress. Of course, these are pre-Trump tariff prices. The Jaiwen XH Star base is nice because it is lightweight and it has not one but two highly visible leveling bubbles which I use during setup. Of course, a level tripod is not a requirement for EQ mode operation, but it does help significantly in achieving a quick and easy polar alignment. If you want a good explanation regarding this surprising claim, watch Astrophotography Japan episode number 25, where I explore this concept very thoroughly. A link is provided in the notes. The first step in the polar alignment is the proper positioning of your equipment. And here I show a view of my S30 telescope, photographed while I was on my knees, looking along the edge of the device which is pointing directly toward the star Polaris to the best of my abilities. This is the starting position and arrangement for your Seestar. I'm not going to run you through the polar alignment menu system. You can view that on one of many other videos that are out there, but we will look at it from a workflow diagram perspective. When you initiate the polar alignment process, the Seestar automatically calculates and goes to a default region of the sky where it takes 3 consecutive images and analyzes those images through plate solving and its polar alignment calculation algorithms. This is somewhat similar to the ASI-AIR all-sky polar alignment process, but not exactly. Frequently, at this starting point, I sometimes get error messages or the alignment process stalls. But every time I have determined the problem was simply being out of focus. To correct this, just run an autofocus routine and reinitiate the process with get polar alignment deviation. By the way, these are actual photos of the 3 imaging points in my polar alignment process. Notice the second image is nearly vertical, presumably on the meridian or close to it, and the other 2 are on either side. This is good. No, this is great for me because it means that I can do the polar alignment process in my backyard, which has a very limited sky view, being blocked by houses on all 4 sides. To the best of my knowledge, you cannot designate the starting position for EQ polar alignment with the Seestar app. It always goes to some default sky region setting. I'm going to speculate that the sky region altitude it picks, actually declination, depends on your latitude. This default starting point feature is different than the ASI-AIR all-sky polar alignment process. In the all-sky subroutine, you can actually pick the starting point for the polar alignment, giving you tremendous flexibility, but not with the Seestar. Fortunately, this restriction is likely just a software limitation, and such flexibility could be enabled by ZWO sometime in the future. After the 3 images are automatically taken, you are provided with some right ascension and declination coordinates that indicate how far off is your alignment from the North Celestial Pole. Also, those coordinates are somehow calibrated to the compass and angular position sensors in the telescope unit. So you can make RA and dec adjustments to your latitude base and see in real time on the Apply screen these numbers changing while you attempt to zero in chasing a perfect alignment to the North Celestial Pole. When you get close, you absolutely need to check that by selecting Get Polar Alignment Deviation again. When you do this, the software goes back to taking polar alignment image number 3 again, which then refreshes the deviation coordinates with some new numbers. The changeable real-time adjustment numbers are not very accurate. However, the first set of deviation coordinates, shown here in blue now, that are displayed after Get Polar Alignment Deviation are accurate because they are based on plate solving and not hardware sensors. Of course, you can continue to repeat this loop, making adjustments as many times as you want until you decide enough is enough, at which point you can go back to the Seestar menu options and go gazing. Now, it has been my experience that sometimes things get a little funky and the numbers are inconsistent and don't make a lot of sense. It can be frustrating. If that happens, it is best to start all over again. The way to do this is very simple. Simply hit that little chevron mark in the upper left of the EQ mode menu screen and return to the previous menu. This will bring up the prior Advanced Features menu page. On this screen, the equatorial alignment process is now reset. So you can select the EQ mode feature and on the next screen hit Get Polar Alignment Deviation. This time, the Seestar will initiate the polar alignment from the beginning by returning to the default first image sky position and then proceed to take 3 new images. This provides you with a new refreshed RA and DEC coordinates. From here, you can continue to make adjustments and do your best to zero in on a good polar alignment. You can cycle through either of these loops until you are satisfied, having found some stable and reproducible numbers. When satisfied, you can simply select the bottom left Seestar icon button and go to the main menu and go gazing. You probably have noticed the first time that you do go gazing on any given night, the Seestar takes 3 to 5 minutes to focus and calibrate itself. After that, it starts collecting target image data. It only takes a few stacked images to see how good of a polar alignment you have achieved. If you find that the stars are consistently oblong and still not round, then your polar alignment is likely suboptimal. You can proceed with imaging if you like, or stop the imaging and go back to the My Seestar page, which is the bottom right icon. From here, you can select Advanced Features again and enter the EQ mode menu to readjust the polar alignment again. When you return to your target for the second time, thankfully the imaging starts up immediately and no new calibrations are required. So visually checking for round stars and tweaking the alignment is not too burdensome. This final workflow diagram shows all the possible loops you can leverage in order to get polar alignment deviation coordinates. In my experience, you have to be very patient, continually making adjustments and rechecking at several stages to really get roundish stars. Now let's talk about my experiment. I had an idea. I was curious. I wanted to see if I could do polar alignment in a different way, the old-fashioned way, with an EQ mount polar scope. Recently, to attach the Seestar to the Vixen clamp on my Latitude wedge, I was using this old adapter that I bought on AliExpress. In fact, I bought this originally for my Skywatcher AZ GTI mount. It came with a polar scope attachment. So here's my experiment. I am going to compare 3 deep sky target images that were captured after using each of these polar alignment processes. First, the Seestar Polar Alignment app, and secondly, after completing polar alignment with a polar scope. I think it is rather amazing how quickly progress has been made using image analytics and plate solving. We mostly do not use polar scopes anymore. I only started this hobby 4 years ago, and at that time, polar scopes were the main way to polar align your mount for EQ tracking. Given this pace of technical advancement, I suspect that some of you watching this video have never even used a polar scope before. Therefore, let me provide a little background on how this is done, with one specific kind of polar scope. Here I am looking through the polar scope to align its rotation axis with the sky and horizon. In this scope is a depiction of the Big Dipper asterism and Cassiopeia. The idea is to rotate the scope so that the position of these star patterns mimic their actual position in the night sky. This functions as a time set. The polar scope must be attached to the mount in that orientation to work properly. Since I will stick this arm out on the left and parallel to the ground, the visual star pattern markings will be aligned to mimic the sky as you see here. After that, to get a polar alignment, all that is required is to adjust the latitude base to move Polaris into the little circle and secure the mount in that position. The actual north celestial pole is represented by the cross mark in the center. It will soon be apparent why I'm telling you all this information in advance. The first set of data I collected was after employing the Seestar Polar Alignment app. You can see here that the final coordinates I got were 0.4 and 0.2 arc degrees, and these numbers were very consistent after several consecutive rounds of get polar alignment deviation and restarting the alignment process. I had high confidence that this was a good polar alignment based on the app. And here are the three images that I collected of M5, M63, and M68. M63 is the sunflower galaxy, by the way, and the other two are globular clusters. These are 30-second subframes, and each is a stacked image with a total of 5 minutes integration time. This particular night, there was a high-in-the-sky 70% waxing gibbous moon, providing a strong sky glow gradient in these images. But since we're only interested in evaluating for star shapes and trailing, the light gradient does not matter. I also determined the distance of each of these targets to the celestial North Pole, and that is listed at the bottom of each of these images. M68 is the furthest away at over 117 degrees and directly to the south. Among the three, the potential for star trailing is greatest on this image. But before we dive into the data, let me relay some critical information. After I took the three deep sky images, I closed the arm and initiated another polar alignment using the app. Much to my surprise, the coordinates I got were 0.4 and 0.2 arc degrees, which corresponded exactly to the values we had prior to the imaging. I expected it to be close, but not that close. Impressive. Then I closed the arm again and attached the polar scope in the proper orientation. And when I looked into it, the position of Polaris was as I depicted here with the yellow star. It was about 45 degrees to the upper left of the tiny perfect polar alignment circle. Another surprise. I expected it to be close to that circle. Now, using the adjustment screws on the latitude base, I looked into the polar scope and adjusted the screws until Polaris was positioned exactly inside the small circle. And then I repeated the imaging again on the same three targets after removing the polar scope. Same exposure times, same settings, same targets. Let's take a look at them. First, M5. Here is the image from using the Seestar Polar Alignment app, and the telescope photo showing it focused on M5. It was to the southeast and just over 88 degrees away from the North Celestial Pole. And now here on the right is the image I took using the polar scope alignment method. Let's zoom in and look closely at the stars. Next, this is M63. Notice its position is nearly straight up to the zenith. Again, like before, the image on the left comes after using the Seestar Polar Alignment app. And here, the image on the right was taken after using the polar scope for polar alignment. Take note that M63 could never have been imaged by Seestar if it was in the Alt-Az tracking mode. there would be too many rejected images resulting from poor tracking, which always happens near to the zenith in the Alt-Az mode. And finally, this is M68, located directly to the south and just over 117 degrees away from the North Celestial Pole. It wasn't very high in the sky at this time. This is a comparison of the two images just as before. And here is a close-up. Look at the shape of the stars. Look for evidence of star trailing. Do you see any differences between these two photos? Now, if you recall, to perform this experiment, I repositioned the star Polaris in my polar scope into the small circle. Originally with the Seestar Polar Alignment app, the error was only 0.4 and 0.2 arc degrees. But after the polar scope alignment, and after the imaging of the targets, I closed the arm and returned to the home position. And then I initiated a new polar alignment with the Seestar Polar Alignment app. The results came back after the plate solving to say I was 0.4 and 3.9 arc degrees off in the alignment. That was quite a bit, so I again attached the polar scope and looked into the eyepiece. And guess what? Polaris was still in the little circle. Being a scientist by training, I felt a need to repeat the experiment again exactly in the same way on the following night of April 8th. I did, and the results were remarkably consistent. But let's just only look at the M68 images in detail, because I think these are typical of all three targets in both nights. Remember, M68 is the furthest from the North Celestial Pole, so any misalignments will appear greater on this target. This slide shows close-ups of the data from both nights of imaging. In my opinion, the stars on the left images, taken after using the Seestar Polar Alignment app, look more round than the images on the right. The polar scope alignment images on the right have stars that appear to be slightly oblong. Not a tremendous amount, but it is noticeable. So my conclusion would be that the Seestar Polar Alignment app results in a more accurate polar alignment than using the old-fashioned polar scope hardware. And frankly, this makes sense. Plate solving is a powerful tool for mapping the night sky. I suspect the error in the polar scope method is in hardware design, like distortion of the polar scope arm, or the Vixen wedge, or other components. It makes sense. Plate solving is software and visual data driven, and polar scopes are a hardware device made with inexpensive components that are also subject to human error. During this experiment, I collected a total of 180 images, 30 seconds each, on 3 different targets. And 120 of those images were used in stacking by the Seestar algorithms for creating a stacked final image. That is a 67% efficiency. And if you look closely at the M63 data, which was collected at close to the zenith, it stacked with 63% efficiency, essentially no different. Now, let me summarize and make some recommendations. The real-time adjustment feature of the Seestar Polar Alignment app relies on compass and angular position sensors, hence inconsistencies are inherent and frequent in real-time parameters reporting. Don't trust the real-time numbers. Use them only as a guide. I recommend that after every readjustment, you check the coordinates again by using the Get Polar Alignment Deviation function. Use your intuition and experience more than relying on the real-time numbers. And if the reported numbers in alignment process give you some bizarre or inconsistent readings, which can sometimes happen, go back to the Advanced Features menu and restart the polar alignment. My polar scope attachment was less accurate than the Seestar Polar Alignment app. I think this is probably going to be a typical outcome for most everyone. The initial sky region selected by the Seestar Polar Alignment app is fixed. It is a default position, so it is not an all-sky application like the ASI Air. Several times when I first initiated an EQ polar alignment on my Seestar and selected Get Polar Alignment Deviation, it simply did not work. The software stalled because it could not plate solve. If this happens to you, it is probably because the stars are out of focus. Exposure times of 30 seconds display minimal star trailing in single frame images after a good Seestar polar alignment. Minimal. It is rare to get perfectly round stars unless you are close to the North Celestial Pole in my experience. Usually the stars are slightly oblong. Frankly, I wonder if longer exposure times are actually feasible with the current low-cost hardware design of the S30. Access to the zenith in EQ mode works great, with frame acceptance rates no different than other sky regions. Under strong moonlight and Bortle Class 7+ skies like here in Yokohama, frame acceptance rates for stacking in EQ mode was generally around 65% and once in a while much higher. But I think the Seestar S30 is highly sensitive to wind, at least mine is, which can dramatically reduce frame acceptance rates for stacking. Its low-cost, plastic-intense hardware design easily gets buffeted by even a gentle breeze, so you should take precautions to provide some wind barriers during imaging. Overall, the new EQ mode polar alignment feature of the Seestar is a welcome new addition to its capabilities that costs almost nothing to implement. Just a firmware update. It works well and provides benefits resulting in higher quality images and fewer raw data files. It is a great option, highly desired by more advanced users, but not required. The Alt-Az mode still works fine, although it has some limitations like tracking targets high in the sky. じゃあ、これから終わりありがとうございます。Here in Yokohama, Japan, I am JPAstroGuy. My name is Paul Cheesegel, and thank you for watching another episode of Astrophotography Japan.